Welcome to the Elemental Journey series, the gateway to entering the world of XRF. In this series of videos, we will talk about the principle of XRF, how to prepare the sample, and some featured application solution offered by us at Malvern Panalytical. My name is Qiaona. I'm the WD Product Manager at Malvern Panalytical. I'm here today with my colleague Lieven.
Thank you, Qiaona. So yes, my name is Lieven Kempenaers, and I'm the product manager of Benchtop XRF instruments. And today, Qiaona and I, we will be talking about basic XRF theory. Okay, so Qiaona, what is XRF? Can you explain what is XRF and how it works?
Well, that's a good question to start with. XRF or X-ray fluorescence is really powerful analytical technique for elemental analysis. And it can be used for all kinds of sample types. For instance, solid sample like steel, for instance, liquid sample, fused bead, pressed pellets from cement. Now, in an XRF spectrometer, the X-ray generated from the X-ray tube will hit the sample and interact with items in the sample. Now, these items in the sample, their electrons in the inner shell will be kicked out by this high energy X-ray. And then the item become unstable. In order to bring the item back to a stable state, the outer shell electrons will fall into the inner shell and at the same time release the X-ray with energy that characteristic for elements. And those characteristic X-ray photons are used to determine the element and later to quantify the concentration of each element. So, Lieven, I know that XRF is not only the elemental analysis techniques. There are also other analytical techniques used for elemental analysis. So why do we use XRF and where XRF is used?
So XRF has many benefits because it's first a qualitative and a quantitative tool. So you can use it for screening. XRF has the benefits of also being non-destructive. So when you have a sample, you can measure it in the XRF spectrometer. And after the measurement, the sample is still there. It's not dissolved or completely burned. Other benefits is that it can handle a wide range of concentrations from pure chemicals all the way down to ppms, microgram per gram, trace concentrations. So many advantages also of high repeatability. XRF can also be automated, can also be a benefit for some of customers who have a big lab where everything has to be automated.
So where is XRF applied?
We're talking about XRF, also talking about elemental analysis in general. There you also see ICP, that's also elemental analysis, which also has benefits, but we see that XRF also has benefits over ICP. So if we look at the elemental analysis techniques where they are used, XRF, ICP, ICP-MS, that is in many industries, where you have to do quality control, process control, R&D facilities for development and research. And that can be in pharmaceutical industry, it can be in the metals industry, and that's also the slide we're seeing here, petrochemicals, food, many industries where XRF can be used as a elemental tool. So we're talking about XRF, and you also explained XRF a little bit, very basic, of course. It's a short kind of a training course.
Yeah.
But what are the different types of technologies within XRF family? We can call it an XRF family.
Yeah. Well, I have to say it's really big family. Generally speaking, there are two types of XRF. Wavelength dispersive XRF and energy dispersive XRF. Very common on the market, of course. Now, under wavelength dispersive XRF, there are also sequential one and a simultaneous one. The sequential one is like a ZTIM. It measures the element one at a time by using a component called goniometer. Now, the simultaneous one is like our axial fast. It measures multiple elements at the same time with what we call fixed channel. So each channel measures one element with one specific crystal and detector. Talking about energy dispersive, there are different excitement source. Now, the most common excitation source is X-ray tube. And that's also what we provide in our EDXRF portfolio. And there we have direct excitation and indirect excitation. And direct excitation means the X-ray generated by a tube directly arrive on the sample without secondary target in between. And just like our product Epsilon and Revontium. You know this better than me.
Yeah.
Now, talking about the difference in the configuration, in a WDXRF spectrometer, there are more mechanical components inside than ED. So there are collimator, crystals in between samples and detector. Now, the collimator will narrow down the characteristic X-ray from the sample to the analyzing crystal. So make sure all the X-rays come to a specific angle on crystal. And then the crystal is used to separate the characteristic X-ray based on their wavelengths. And after that, all the X-rays will enter the detector and later processed by, for instance, amplifier and multi-channel analyzer. And that's about WDXRF. It's mechanically more complex than ED.
Yeah.
Well, for ED, it's mechanically simple. The main components there are tube and detector system. So there we get the characteristic X-ray from the sample, and they directly goes into detector. So the detection system for EDXRF is very critical because it's used to separate the element based on its energy and also processed later to get the concentration result. As a product manager of WDXRF, I do prefer WDXRF. So how about you, Lieven?
Well, I see the benefits of both.
Okay, that's fair.
I prefer EDXRF.
Okay.
For many reasons, but WDXRF and EDXRF, they have both their advantages and also disadvantages.
Yeah.
And I think it depends on what the customer really needs.
Yeah.
Is it sample throughput? Is it low cost of operation? Or the customer has a low budget, only a few samples to measure in a day, then he doesn't have to buy the Ferrari.
Yeah.
So you explained the difference between the techniques. So when you look at wavelength dispersive instruments, they are bigger and better. But as you said, they have more mechanical components. There's also a reason for it. They also have a higher power. Of course, they also need to cool for that. But of course, the resolution is much better, especially for the light elements.
Yeah.
So that also depends on what the requirements are of the application, what is necessary. When you go to the benchtops, the smaller units, there it also again depends on what is the requirement. if you only have a few samples, if you have a limited lab space, then a benchtop is good enough for the job. For a few samples, it doesn't need extra cooling. It fits on a table, and yeah, the maintenance is also lower because there are less moving parts.
Yeah.
So, pros and cons on both techniques.
Well, I have to say that's a fair competition, even though you say you prefer ED. But let's just quickly wrap up what we have discussed in this video. First of all, XRF is powerful analytical technique for elemental analysis, and it covers a really wide range of elements and also very large concentration from sub-ppm to 100%. Now, the sample preparation, as you mentioned, is very simple, and compared to other techniques for elemental analysis, and also the throughput and the speed is much higher, and that's why it's very widely used in production for quality control and process control. And you also mentioned XRF is a non-destructive technique, and that's why it's also preferred by R&D for research, because they may use the sample later for other analysis, and sometimes the innovative material are really little, so they have to keep it for different techniques. I believe you know that XRF is not an absolute analytical technique. So it means it needs some calibration standards in order to get the concentration result. And that's something we're going to talk about in the next video.
Okay, good idea.
Yeah.
Yes.